Good morning, everyone. I'm Dr. Rakeshina. Now I'm going to present phase shifting impedance matching network. So before starting this presentation, I would like to start my presentation with a quote of Professor Albert Einstein. To raise new questions, new possibilities, to regard old problems from a new angle requires creative imagination and marks real advance in science. So this quote I am reading in the perspective of phase shifting matching network. So matching network has been known for several years and it has been well known for the RF and microwave engineers. However, the concept of including phase shift in the design of matching network was not there. So in this following paper, I introduced that concept of including phase shift in the design of matching network. And this is a software which I have developed. Using this software, one can easily design a desired phase shift impedance matching network for desired load and source impedance. And this software is freely available in Zeno, and it can be downloaded. It can be downloaded by anyone, and then they can directly use that concept, and then they can design their own desired phase shift impedance matching network. So before starting the concept of matching network, I would like to start with that maximum power transfer theorem. So what does it state? That you have a source with ZS source impedance, and if it is connected to load ZL, if this ZS is complex conjugate of ZL or this ZL is complex conjugate of ZS, then we can deliver maximum power to the load. If the load is real, then in that case your source must be real and equal. Okay, so there is no conjugate thing is required. Okay, so they are equal in case of real impedances. Now this is a graphical solution of maximum power transfer theorem. So you can see here. So when your load is very small or towards the short circuit, so your voltage drop is almost negligible and maximum current is flowing. And when the load is towards the open circuit or very high, so in that case your voltage is maximum and current almost goes to zero. So there is no power. Okay. And in between there exists a region where you have an optimum or maximum power transfer is occurring here. So you can see here that at 100 ohm, so because RS is 100 and when RL is 100, so in that case we can see the maximum power is delivered, and that maximum power is depends upon your voltage and your source resistance. Now if your load impedance is not complex conjugate of your source impedance, then what is the solution? Solution is basically you can include a impedance matching network, which is basically lossless reciprocal two-port network, which basically convert this load ZL into complex conjugate of your ZS. Or in the other word, I can say this source impedance is converted into complex conjugate of the load impedance, and vice versa. Now, the earlier design of matching network was performed based on this conjugate property. You can see here, if you equate my this side impedance at the source side impedance and the load side impedance and equate them in terms of the conjugate, this conjugate of each other. If you equate them, you can get the design equation and you can design the matching network. So this is an example of designing matching networks or for load of 10 ohm and source of 100 ohm, and you can see it has been designed for 1K, and you can see that at that frequency point you have maximum power is delivered to the load. Now there are several solution exists. This is not an unique solution. So you can design a pi network with different choices of this capacitor, inductor, and thing, and we can have multiple number of solution. Now that this multiple number of solution can be explained in terms of the Q of that matching network design, and another way is basically based on the phase shift. So you can design a particular matching network for a desired phase shift. Now this is an example of step impedance matching networks. You can see here. So we have different load impedance and source impedance. So in this case we have chosen 100 minus J30 is the load and source is 50 ohm, and we have designed multiple number of solutions, 6 number of solution, and in each and every cases what we can see that phase shift and the electrical length are different. They are not same. In many cases people say just like that the phase shift is beta, so that is not correct. So that is true under the condition if the source and load are terminated by the characteristic impedance. And we can see here that we can achieve different phase shift by choosing different parameter, particularly different parameters. Okay. So this is the scattering parameter response. So every matching network having different kind of bandwidth response, and then their phase shift response. Okay, and depending upon the requirement, we can choose a particular phase shift response, particular phase shift, whatever is required for the design. Okay, so the importance of matching network, phase shift in the design of matching network play when you are utilizing multiple matching networks. Okay, so this is an example of two element phased array. So we have designed two different matching networks for two different impedances, Z antenna 1, Z antenna 2, and this got provided into different phase shift phi 1 and phi 2. So by looking into that phase shift, we can can say about the phase difference between the element, and then we can predict the direction of the beam in terms of the transmitting antenna and receiving antenna. Okay, so we can easily figure it out in which direction the beam will come, or basically beam will be directed. Now that I have devised this symbol for representing a matching network. So this ZS is the source impedance, ZL is the load impedance, and phi is the phase shift. Okay. Now typically the reflection coefficient of matching network is basically equals to 0. So that means basically the transmission coefficient is 1 because the matching, there is no loss, internal loss in the matching network itself, ideally. So as we are inserting the matching network between the source and the load, so obviously it will provide some kind of delay. Okay, so that delay was not previously taken care into account. So we have past time shown that okay, you can incorporate this delay in the matching network, and we can design for our desired phase shift. Now the two port scattering parameter of the matching network can be characterized as S110, S220, S12 and 21 are basically unity in terms of magnitude, and the phase is basically phi. Because it is a reciprocal device, so S21 and 12 are the phase of S21 and S12 are identical, so there is no difference between them. They are equal. Now we cannot utilize this direct scattering parameter equation for the design. So what we can do, we can convert this scattering parameter into ABCD parameter. So this is a closed form expression for the ABCD parameter of a matching network. So once we know my ZS, my ZL, my phi, desired phi, so we can basically get my ABCD parameter. Once we know the ABCD parameter, so we can basically design the desired matching network for a given topology. For example, let's say we are designing a T matching network, lump T match network, so which consists of a series, shunt and series element. So you have a series element, shunt element, and series element. So if you multiply them, we can get the closed form expression for the ABCD parameter. Now if you equate that with the desired ABCD parameter, then we can get the design equation for the susceptance, reactance and reactance. Okay. And then from this susceptance and reactance, that can be converted into inductor and capacitor at the design frequency. Okay, thank you for listening. The details of this lecture will provide later on. Thank you.